And I can't not talk, so I'll find something to talk about. Probably, all right, I have to think about it. Probably what I would be doing on Wednesday if it were ideal in a full class is starting to switch over into using computers to make things go fast. And talking about how we measure things like, terms like scale up and scale out and speed up and diminishing returns on how you can make things go faster by using multiple machines. Like, who's studied like Amdahl's law in the context of parallel or architecture? Yeah, so I might go over Amdahl's law, so good, you all know that already. It applies importantly in the context of distributed systems for similar reasons, right? But today, I'm tired and I want to go slow, and I want to do a little bit of recap because we went through a lot of definitions last time. So I want to recap, like, what is the serializability thing all about? Why am I teaching you about serializability, this concern that sort of arises on single-site databases and sort of is arguably orthogonal to distribution, okay? In what ways is it similar to or different from notions of correctness that we have studied in the class? So I want to try to make the connection a little bit more clearly. I want to spend a little bit of time recapping two-phase locking in the context maybe of a running example or something. We can go slow and take our time and ask questions. And I wanted to give more details about optimistic concurrency control because I ran out of time last time. Right? And then we'll probably not talk about databases anymore. Except to point out that, as I did on Friday, the thing that you are building in this course incrementally very much resembles a database, right? Modulo we haven't implemented transactions on it yet. That might be like homework 4, but maybe you can begin to imagine now how you might layer transactions on top of the system, like the key value stores that you all have been building. Obviously, we're not supporting a rich query language, but you can imagine that as homework 6 to support like doing SQL over these databases. I was just talking to students, one of the reasons that we do this assignment is that when you get to homework 4, and spoiler alert, what you're going to do with homework 4 is you're going to take your causally consistent database and you're going to scale it. So just to say, like, that database is great, it's fault tolerant. If you throw more computers at it, it gets more resilient. That's dope. But you know what would be even doper is if you throw more computers at it, you can make it go faster and have more capacity to store more data. And so you're going to do that by, I want to be really careful with this word partitioning, because the word partition is overloaded, but sharding the data across multiple replicas, right? So each key belongs on one particular group of replicas, only one. And that way you can increase the capacity of your system as well as its fault tolerance in 2 different dimensions by adding replicas. The reason I have you do this assignment is that when you're done, you will have implemented a NoSQL store like the cool kids used to 10 years ago. And it'll give you something to talk about in your interviews. People interviewing you are going to be familiar with causally consistent systems that achieve fault tolerance through replication, that achieve scalability through partitioning or sharding. You're going to have a lot of good stuff to talk about the different design decisions that you made since we didn't restrict the design decisions. So that's my hope, is that this is like something for you to talk about in your interviews. Yeah?
Are you saying that NoSQL is not cool anymore?
I didn't say that, but I'm pretty sure I implied that, right? I mean, no, you know what's cool now? SQL is cool again. and seriously, so, am I repeating myself? No, we talked about this in office hours. There's these pendulums that swing in systems. And they usually swing on a cadence of like 10 years. And so one of the pendula that I'm most interested in is consistency, right? So like in the early 2000s, after this explosion of peer-to-peer systems, where all of a sudden people started being like, whoa, your distributed system might have like 10,000 nodes in it. Not like 3 or 5, 10,000. So things start to not scale to those sizes. Like, it wouldn't make sense to do primary backup replication if you had 10,000 backups, right? So right around the early 2000s, people started to say, the limits of scale, as computers are web scale, they're spread all around the globe, it doesn't make sense to have strongly consistent systems and serializable systems anymore because you pay too much. It costs too much to do access. It costs too much to do locking. So we need to explore this space of weakly consistent systems so that you can go fast and so that you can understand what you can get away with doing wrong, given that when you have weaker guarantees, things are going to go wrong. And so for 10 years, that's all anybody did was come up with systems that provided like fragments of what a database provides, and then seeing what they could do with that system. And you've heard of these systems, right? Mongo, and Cassandra, and React. And then right around 2011, Google started publishing papers, like the Megastore paper, and then the Spanner paper, where they're like, hey, exactly the opposite of what you were hearing 6 years ago. Like, hey, weakly consistent systems are cool, because because they're like cheap or whatever. But programmers really want stronger guarantees, you know? And if you give them a serializable system, they don't have to worry about, in fact, let me draw a little picture. I'm going to talk about this today anyway. So what did the bad old days look like of strong, you know, applications built on relational databases that were strongly consistent that provided serializability? You had this really big relational database that had a ton of logic in it, right? Because this database, in order to provide an API that provided serializability and recovery, had to anticipate everything that could possibly go wrong and work around it in a way that was transparent to the app. So you could be like this happy-go-lucky app developer interacting with a backing store that was a Oracle or something like that. And you could just, in the app, pretend that the system never crashed and that there was never any concurrency. Because serializability meant that although there was concurrency, right, you couldn't perceive it, you couldn't witness it. So you could just write this really thin, simple app and nothing could go wrong. Then people said, okay, well the DB was too slow. So now what we're going to do is we're going to have these no DBs, which are significantly shallower stacks and provide significantly less guarantees. And that meant that the application developer now had to write these big honking apps that literally like had code branches for, oh yeah, and if that replica you're trying to talk to isn't there, do this other thing. And, oh, by the way, if somebody stomped on that value after you read it, but before you wrote back something else, do something else. And if you recover from a crash, here's how you replay your log to get back to some good state. Like all that logic used to be down here, and now it's here. But it's worse than that, because somebody else wants to write an app, and they have to do it again, and again, and again, right? So that's not scalable either, in a totally different way. And so talking about what we're scaling. Are we scaling the system and trying to be fast, or are we scaling like the humans? It's something that I haven't brought up before in this class, but it's very often the case that we forget to realize that the biggest cost usually that we pay in computer systems is paying people to write the damn software. Because we make a lot of money. You know, you could just have 3 people implement everything. Hey, who's ever heard of K-version programming? Oh, I have to go off on this for a minute. Okay, so replication is this thing that we do with our data to guard against the crash of a machine. Okay? And as I indicated when I gave this lecture about, right, about how we place our servers in racks, and the racks have top rack switches, and they communicate with each other, right? So servers could crash, but also the top rack switch could crash, and also a power supply connecting multiple racks could be lost, right? So when we thought that by putting our data on 2 machines, we were taking the probability P and squaring it of a failure, that was only under the assumption, like we can only multiply probabilities when the probabilities are independent. Right? So we were assuming that the failure of X and the failure of, let's say, Y, sorry, are independent, but they're not. Right? So you have to keep asking, where is my, but I could get independence if I put Y in like a different data center, right? Assuming that they're far enough apart that a hurricane couldn't hit both of them. Right? So you have to keep asking yourself, like, I'm predicating my estimation of how resilient my system is based on some fundamental assumption about independence. And you have to ask yourself, where does that fall down? Right? So let's imagine a world in which you could, there was actually a data center on Mars, and you could get your data to Mars, and the latencies were okay. You know, we're gonna have problems with intergalactic access for obvious reasons, right? But maybe entanglement will solve that for us by the time we actually have people out there. So let's say that you could get it on Mars. So it is truly independent. There's no, you've probably heard this term before, there's no correlated single event failure that could affect my data centers on Mars and Earth. So I can say I have p-squared likelihood failure. That's not true, because there's still a dependence. What is it? The software. Yeah. Right? If there's a bug in the fucking primary backup replication, that bug's on Mars too, buddy. Right? So, but we're fucked, right? We're fucked, right? Because what are you gonna do about that? You gotta run the code. What could you do? Right, well what you could do is, you could figure out the API for primary backup, like the most abstract, right? What is the externally facing API? And then you could go to 3 completely different companies in 3 different countries that never talk to each other, and you could have 3 different teams of engineers, this is algorithm 3, algorithm 2, and algorithm 1, implement different implementations of the same API. If they didn't talk to each other at all, and they didn't read the same books, They weren't in the same class, learned the same bad ideas from the same professor or whatever. Then you actually do have a shot that the implementations are independent in the sense that a bug is vanishingly unlikely to be the same bug in multiple implementations. So what do? Well, then you run all of the implementations as an ensemble, and then you have them vote about what the answer is. That works. This is like Socratic, right? Why do you think we don't do this?
Expensive.
That costs 3 times as much of the most expensive part of the system. It's not the servers, it's the person implementing friggin' Paxos. That costs, implementing Paxos costs like $500,000, right? Probably. A few engineers, 6 months. Easily it does. So, this is, 3 times as much. But some people pay this cost. Who pays the cost? What kinds of industries, what kinds of applications would you be willing to pay the cost for like true independence, even if it's like, what do you think?
Thanks.
Yeah, for sure. Aeronautics, broadly speaking, right? So flight, planes, right? It's worth it. How does a flight control system on a plane work? You have 3, usually, or you usually have 5, independent computers, very often different physical computers with different physical hardware, certainly the hardware bought from different vendors at different times, right? Because independence. And then you have different implementations of the Byzantine fault-tolerant consensus algorithm running on all the damn computers. It's worth it. I mean, safety is so important to airlines that all pilots aren't allowed to fly until they have some thousands of hours worth of simulation. Imagine what it would be like if we applied that kind of rigor to software engineering. Like you wanted to be an SRE at Netflix, and it's like, cool, we're paying you $500,000 a year, this is Netflix, right? Before we let you touch any code, we're gonna make you take 2 years and like watch videos of outages and see everybody running around putting it out. Nobody would pay. So it's gonna cost $1.5 million to ramp somebody up before they start writing some stupid web app. Like it doesn't make sense, right? Anyway. This is just to say 2 things. Software is very often the big hidden cost, right? And independence, which is required to do this kind of reasoning, is elusive. It's very hard to get true independence. Okay, and then this was all to say, 15 years ago we were here, 8 years ago we were here, and now we're here again. Because Google's publishing these papers saying, this is too hard, programmers' brains aren't big enough to do this, they want to do this. We figured out a way to make it sufficiently fast. And all those things people were saying 10 years ago about transactions not being web scale don't seem as true. Yeah? Good? Let's recap serializability.
You said that's called K-version software or something?
That's called K-version programming. That's right. Where, K is for 5. Yeah.
Is that what NewSQL is?
Yes. I mean, these are all just buzzwords, right?
Yeah.
But I think like a lot of people like me, people who are like professors who do databases, started coining this term NewSQL, meaning recovering those strong guarantees, maybe using some state-of-the-art replication techniques and stuff like that. So NewSQL databases, unlike traditional SQL databases, tend to be distributed. That's like one big difference. Like you're running on a great many machines. Okay. Does somebody want to give me a high-level gloss for what serializability is before I remind everybody of the formal definition in terms of some of the terminology we introduced on Friday? What is serializability?
Well, maybe it's part of the problem you can split up across nodes.
Well, sorry, say that again? So
The portion of some problem you can split up across.
oh no, I think that's interesting that you say that. I think like what you're describing is at least the syntactic opposite of this. That would be like parallelizability. Yeah.
Is that you have a couple of transactions and you want to kind of like encapsulate them into an isolated environment?
So serializability is going to be a theory that allows us to reason about a really important property that I call isolation, right? The illusion that I have exclusive access to the database for the duration of my transaction. So in some sense, isolation is like a word for what serializability gets us. but not really about exactly how or why. Yeah.
We define serializability as actions which are performed in the same order or with the same outcome across multiple machines.
Well, with the same order or the same outcome as what?
As all machines that action is being done on.
Well, I think the important part is to say a schedule is serializable if it has the same outcome or has the same order of conflicting operations, exactly as you say, as a schedule that there was no concurrency in, right? Because what do we want? Isolation. What's isolation? There appears to be no concurrency. So one way to get isolation is to have there be no concurrency, right? So if we ran all the actions, remember transaction 1 might do a lot of different reads and writes. If we did finish all the actions of transaction 1 before we start transaction 2, then there's no concurrency. So everybody agrees that if we did it like this, we had isolation, right? Anybody disagree? Okay, so a serial schedule is surely isolated by schedule. What's wrong with it? Hold on a second. Schedule. God. So a serial schedule tautologically is isolated because all isolated means is no concurrency, no visible concurrency, and this has no concurrency at all. So obviously it has no visible concurrency. Okay. We're going to say that some other schedule in which, for example, maybe the actions of T1 overlap with the actions of T2, heck, and T3. This, we might have reason to worry because obviously there's concurrency. We're worried that T2 might read something that T1 wrote or fail to read something that T1 wrote. If T1 writes something out here and T2 didn't see it, then we can't say that the outcome is like T2 happening after T1, right? If T2 happens after T1, one thing we know for sure is that T2 is going to pick up all the breadcrumbs that T1 drops. But if we have an interleaving like this, and the guy dropped a breadcrumb here, we could have a problem, right? So when do we know that a schedule like this is like cool? If we can prove that it is equivalent to some serial schedule, because if it's equivalent to some serial schedule, you can't tell that it wasn't that serial schedule, and any serial schedule is okay because there's no concurrency. So everything that you said, except it's all about. And so we said, what do we mean by equivalent? Well, we could mean two things. We could mean like looks the same, and that's what I call view equivalence, right? That's really what we want. And by looks the same, what do I mean? It's two things. Looks the same to an outside observer. So what are the things you could observe?
Like the outcome, or I guess the
yeah,
values.
like the final state of the database,
right?
And the values returned by the reads, right? Because those are the two visible things of the transaction. What it does to the store, and what it kind of takes out of the store. Yeah?
So, can you explain the difference between the final state of the database versus like end values of the reads? I kind of
sure.
I,
I mean, just picture a database. And there's some clients. Oh, there they are now. Okay. And this guy does it right, x is 0. Well, then I care about the fact that at the end of the day, x is 0, even if there's no reads. Similarly, even if at the end of the day, x equals 1 and that's what it's supposed to be, I care about my reads that I did along the way.
I see. Okay.
So you imagine the union of the database state and the results returned by all the reads, which don't necessarily land in the database. They land on clients, and they reflect the state of the database at a particular moment.
Right.
It might have been correct or not.
Okay.
Does that make sense?
Yeah.
Questions? Yeah.
So T1's running while T1's running start T2, and if that outcome is the same as if...
Yeah, so for example, according to view serializability, if after we've done this whole thing, the end state of the database is the same, and also any of the reads are the same. Like if this guy read a 7 at this point, this guy better have read a 7. If both of those things are true, we say they were equivalent. And in some sense, that's like really what we mean by equivalent. Indistinguishable. Unfortunately, as I discussed, view equivalence is too hard to compute. Because what a concurrency control algorithm is going to try to figure out if a schedule that we're learning about over time is going to be serializable. And if it's not, it has to either delay, be like, oh, T3, you can't even start. What are you doing? You have to start over here. Because if you start over here, you're going to read something too soon. Or it has to be like, oh shit, you read something too soon, so I had to abort you, and now you have to start again way out here. So that's what a concurrency control algorithm does. It tries to continually ask this question, is this schedule that I'm like learning about as transactions enter the system going to be serializable? And if not, how do I prevent anything from seeing something like that? So as a consequence, that algorithm needs to be computationally efficient. It has to run faster than the database is doing anything else, right? Or else you're just waiting all the time, not admitting. Like, if this were slow, the marginal benefit we get from interleaving concurrent transactions would be squandered, right? So instead, get, let's see. I was going to write that more clearly, but conflicting operations happen in the same order. And by the same order, same with respect to what? Well, the conflicting actions in the interleave schedule happen in the same order as the serial schedule to which they're supposed to be equivalent. Right? It turns out that this one's easy to implement because we can just lock things before we do operations on them. And then if there is a conflict, the lock will have decided what happened first. Right? The guy who got the lock, guess what? His operation happened first. Two-phase locking is going to be a locking discipline that enables us to sort of just get serializability for free based on the order in which we acquire our locks. Maybe it's worth now taking an example. Let's see. Let's say I had a database. Let's say I had a couple transactions. There's one transaction that was trying to put something down. Huh?
Well, you forgot the word order on the number 2.
In the same, oh, yeah, look at that. In the same order. Right, so just, and to recap the definitions, a schedule is an ordering of the atomic operations in transactions, or the reads and writes. We say that two schedules are equivalent if one of these two things is true about the two schedules. A serial schedule is a schedule in which all transactions complete before the next one begins. And a serializable schedule is a schedule that is equivalent to some serial schedule. The touchstone for is correct and makes sense appears to be, isolated. No, that's not right. Oh, here we go. Let's say that I had this one transaction that wanted to read X, then read Y, and based on the values that it read from X and Y, it's going to write Z as 1. So imagine that we had another transaction that would like to run concurrently that tries to, read X also. And then it just tries to write something to Y. So let's visualize it. So I have T1 out here. And let's imagine that X started out with some value 0, and so did Y, and so did X, so did Z. The transaction one says, all right, let's read X. And so before we even get into the logic, what are we worried about, right? I guess one way we might say what we're worried about is, we're worried that given these two transactions, I haven't said anything about what values they actually read, what values they got back from the database. But bear with me, because I haven't really thought this through. What we're afraid might happen is that T1 reads X and learns that, I don't know, it's 0. And they read Y, and they learn that that's 0, too. And then they write Z equals 1, and they're happy. Now, because T2 wrote Y equals 1, if T2 happened first, could T1 have read these values?
No.
No, not unless somebody else came along and set it back to 0. right? T1 would surely have read that y was 1. So if the serial schedule is T2 followed by T1, then we would expect that, that T1 would not end up reading zeros. In fact, the fact that it read zeros implies that T1 must have happened first. And so what we're afraid of is a world in which, because we've done concurrency control incorrectly, T2 comes along and reads x is 0, or x is, sorry, no, T2 reads y, no, z. If T2 read z is 0 and then wrote y is 1, do you see how this couldn't have happened in any serial schedule? Or should we take some time to look at it? Yeah, okay, so if let's imagine, so do you buy it that there are only 2 serial schedules? T2, T1, and T1, T2. Okay, so let's talk about what it would look like if T2 went first, right? If T2 went first, what would it do? It would read z equals 0, and it would write y equals 1, right? And then when T2 came along, what would happen? It would read x equals 0, and it would read y equals 1, and then it would write z equals 1, and that's fine. T2 would better not read z equals 1, because it came before. It read z equals 0. So that's fine, right? So that was T2, T1. And then over here, what would happen if we had T1 and then T2? Well, T1 would read x equals 0. I know I'm blocking for some of y'all, in a sec. It would read y equals 0, and it would write z equals 1. And then T2 would come along and say, oh, no problem. I'll read z, what? 1. It's 1. And then I'll write y. Okay. 2 serial schedules, 2 final states of the database and returns of the reads. You see how neither of them allows T2 to come along and read z as 0, and nevertheless to let T1 also read that y is 0. Okay? Does that make sense to everybody? Any questions about that? And why is this bad? Yeah, because both T1 and T2, or at least one of T1 and T2, has evidence of the fact that they weren't isolated. Of the fact that I got into the database, I opened my transaction, I started doing shit, and then I saw the database change underneath me, which means I was not the only person in the database. And all serializability, you had one job, and it was to preserve the illusion that T1 and T2 are both the only people in the database, even if it means making one of them wait or abort. Questions? It's important. Everybody feels comfortable? Okay, good. So then now the question, of course, is how would something cute like that we feel like we understand, like locking, solve all these problems? Okay. Let's look at it. So T1, let's say that the first action, it's T1. It's going to turn out it doesn't matter. It's always going to turn out. But we can't explore every possible schedule. So what's T1's first action? It's going to obtain it's going to obtain a read lock on X. And a read lock is compatible with what?
Read locks.
Read locks only, right? So then the thing comes back and says, yeah, sure, X is 0. Okay, that's fine because T1 always reads X equals 0. So nothing interesting has happened yet. T1 reads X equals 0 in both the good and the bad executions. So we don't know what's going on yet, right? Now, you class, tell me what the next, so this was action 1. What do you want the next action to be? This is a parallel concurrent system. It can be anything. Well, it couldn't be anything. It can either be this or this. Well, it's up to you. I mean, pick something. Yes.
Y.
Make a, read Y? Okay, sure. So then he says read Y. We obtain our read lock on Y. We get Y is 0. So note that now, like, we're potentially in trouble. The fact that we read Y is 0 means that T1 had better be scheduled before T2 for all conflicting operations, because in our equivalent serial schedule, T1 definitely comes before T2. We know that already, right? Because it read the initial value of y, and had it been scheduled after T2, it would have read 1. Right? No? Yeah? Okay, good.
You don't release the locks though.
Nobody's releasing any locks, no. Heavens no. Not yet. Not till commit time. Okay. Now, what's the next thing that happens? So note that this means that we're going to have to either slow down T2 or abort one of these guys. And I think with this example, different ones could happen depending on what order the operations flow in. So what do you think should happen next?
Read Z.
Thank you, because if we got here, then that's trivial, right? Then in fact, we had a serial schedule.
Serial.
Right? Thank you. Okay, so we said this was 2 and this was 3. So what's going to happen? So here we have T2. They're going to come in here and say, let me get Z. And it's like, uh-oh.
You have a deadlock.
Not that.
So we have a read lock on Z. Okay. And now what do we want to do?
Get a right lock or
Should we do this or T1 or T2's next action next?
T1.
T1? Okay, so let's say this is number 4. So T1 says, cool, let me go ahead and get a right lock on Z. Well, that's not going to work, because there's already a read lock on Z. So T1 is going to hop into a queue behind that lock and wait for her chance. But she's going to be waiting for a long time, right? Because what happens next? So then this gets scheduled. Now, no, just intuitively, when does T1 get to go? When T2 commits, because T2 holds a read lock that will not be released until commit time. So T1 gets to go first the very moment that T2 commits. Right? So T2 comes in and says, or no, T1 comes in and says, so yeah, they're in queue. And then T2 says, okay, now I would like to write Y is 1. And what happens?
Q lock.
Yeah, so now T2 is sitting in a queue waiting to obtain its write lock, which is incompatible with the read lock that T1 already holds on Y. So this is what we call, sometimes more colorfully in the community, as the deadly embrace. Seriously, I'm not even kidding. Because we have the situation in which we might draw in the following way. We might say T1 waits for T2, and T2 waits for T1. And these two philosophers are not eating dinner tonight. So, but just since we got here, so obviously, like, one of the ways that you can deal with a conflict, even in a locking discipline, is to abort one of them. Aborts also enforce waiting, just a good deal more waiting than a lock typically does. How do we detect deadlocks in a database? What algorithm that you studied in 101 would we apply to determine if our database has a deadlock? Yeah,
A graph algorithm.
sure, but which one?
If Dexter's goes
Huh?
negative.
Well, DFS, yeah, DFS might be what you're trying to do, but what is the problem that we're trying to determine? Yeah.
You want to try to find a cycle in the graph?
Yeah, so strongly connected components, right?
Right.
Strongly connected components. And so DFS might be how we explore the graph or BFS. And then, but then typically, how do we do strongly connected components? You guys, do you guys study this?
Dexter's
Closer run
great,
result.
right?
Very often you just use like a label propagation algorithm, right? You pass around labels of the nodes that you've seen in your depth first or breadth first traversal of the graph, and you accumulate those nodes at all the nodes. And if there's any node that has like seen itself on the walk around the graph, then you know that that whole set of nodes in that label is a strongly connected component of the graph, right? So we have good, efficient algorithms to determine if a cycle exists in the graph. Although I should point out that in a distributed database, the problem might be non-trivial because some of the edges of the graph might be on one shard, and some of the others might be on another shard, which means that deadlock detection is the kind of problem that you would want a globally consistent snapshot to answer. You'd want to go say, what is the state of all the nodes? And is there a graph in that distributed state? Or, sorry, excuse me, a cycle in that distributed state. Okay, that's how you detect a graph, deadlock. What do you do about it though? What should we do?
Abort.
Okay, so we should choose a victim. Right? In fact, that's the terminology.
Victor.
One who hasn't done a right
Like
yet,
that.
we can kill that one.
Why?
Does it mean not do anything?
That's an interesting one. Problem with that is,
Then
what if you were a read-only transaction in a write-heavy workload? You might just get aborted over and over and over and over again. So when we choose a strategy for victim choosing, one of the things that we want to avoid is this notion of like starvation, right? Like it wouldn't be fair if some poor transaction just gets the doo-doo end of the stick like every single time, right? So how might you make sure that your deadlock, what do you call it? Deadlock remediate, deadlock, not deadlock avoidance, but deadlock remedy, yeah, amelioration. I'm drawing a blank on the word. Your deadlock amelioration algorithm is starvation free. How would you do that?
pick the one who's been run the least amount of time, the least amount of time.
Good. Yeah. Oh, you all read your Aeschylus, right? You sacrifice your youngest daughter. You kill the youngest transaction, right? Then transactions that have had a few bad runs around this thing get a chance to finish. This is akin to the way we used numbers in Paxos, right? Where we were kind of using them for the opposite reason then, is that in Paxos we always wanted higher numbers to win, because we always wanted a relative newcomer to be able to make progress, because the old timers might be dead. Whereas now this is like the dual of that. We're saying, no, the smaller numbers win, because you want an old timer to have the chance to finish. Yeah? So what would happen is, T1 would wait, T2 would begin waiting, they'd wait for a while. And this asynchronous process that was running on the background, taking snapshots and running connected components algorithms on the snapshots, would decide that a deadlock existed, choose T1 as the victim, abort T1, and then give T1 a chance to start again. Now when T1 starts again, what number should it get? A new number, yeah. T3, right? Okay. Actually, no, that's not true. It should have kept the same number, so that it has a chance to win. I had that backwards, sorry. Okay, good. That's deadlocks. Let's talk about OCC. Oh man, so my family's in town for the whole week. And I was like, when I was coming to class, I was like, I'm going to class right now, but I got out at 3:45 and I'm running down the hill, y'all want to go to the beach. And it's like, I got a maybe from my 8-year-old, a yes
You got a
from
phone?
the 3-year-old, and my wife is on the fence. Leave my beach hating family? No, I'm gonna go by myself. There's like no time to lose. We've got like 30 minutes before the sunset. All right, good. All right, OCC. I don't want to spend too much time on OCC because I want to talk about session guarantees. Sorry. OCC proceeds in 3 phases. I began to do this the other day, but I didn't finish. There's a read phase, in which we fetch data from the database, just like we would in 2PL, except that we don't get clocks, right? There's a validate phase. Oh, and then while we're doing our reads, we're staging our writes locally, right? Remember?